Hey genius, welcome back to the third lecture of periodic table and periodic trends. So in the previous lecture, means in the second lecture, we have learned about history of progress of periodic table. In that second lecture, we discussed about law of triads, rule of integral multiple, law of Telluric screw, law of octaves, limitations of law of octaves, as well as we have discussed some important things on Mendeleev's periodic table, comparison of properties of group 1a and 1b in Mendeleev's periodic table, and we have also discussed some usefulness as well as defects in the Mendeleev's periodic table. So these many things we have already discussed in the lecture 2. So if you have not seen the lecture 2, please go and watch it. And in this lecture, we are going to learn about discovery of noble gases, discovery of atomic number, the modern long form of periodic table, and advantages as well as defects in the long form of periodic table. And towards the end, we will briefly discuss about Bohr's classification based on electronic configuration and the actinide hypothesis. So, without wasting any time, let's start. So, the discovery of noble gases came into the picture in the time of 1894 to 1898. Using two different methods to remove all known gases from air, Ramsay and Rayleigh were able to announce in 1894 that they had found a monoatomic, chemically inert gaseous element that constituted nearly 1% of the atmosphere. They named it argon. So Ramsay discovered argon in 1894 with Rayleigh, and after that he discovered krypton, neon, xenon in 1898 with Maurice M. Travers. And another noble gas element, radon, was discovered in 1898 by Frederick Ernst Dorn. Now in 1913, discovery of atomic number was done. So in 1913, Moseley discovered that atomic number instead of atomic weight is the fundamental property or the identity of an atom. So based on this, he proposed his periodic table. So basically, he had worked on characteristic X-ray and atomic numbers. So before this time, so scientists and the researchers, they were arranging the periodic table according to the increasing order of atomic weight. But atomic weight is not the sole identity or inner property of an element. Actually, the atomic number, that is the indistinguishable, or that is the main property of an atom. So that's why Moseley first said that atomic number uh, he discovered first, and that is the fundamental property of atom. Now, in 1922, the modern long form of periodic table came into the picture. That is also known as Bohr's table, because Bohr created his own version of this table in 1922, and based on experimental measurements of electron energies, along with some guidance from the periodic law. So Bohr's table added elements discovered since 1869. Now let's see the modern periodic table. So this is a version of modern periodic table where you can see we have 7 periods. So if you see these rows, these are actually called as periods. Row wise, these are called periods. And if you see the columns, those are called groups. So in the modern table, there are 18 columns or 18 groups and 7 periods. Now we have metals on the left hand side in this periodic table and non-metals in the right hand side. So these are the non-metals. So I will say these things in details in the later lectures. But for the time being, you just know, so this is the borderline. These are called metalloids, which consists some property of metals, some property of non-metals. These right hand sides, they are called non-metals, whereas left hand side portion is called metals. Now these are the group 1 and group 2. They are called S block S block elements. Whereas if you see from 13, group 13 to 18, these are the P block elements, and this group 3 to group 12, these are the transition metal elements. Whereas inside this group 3, we have this lanthanides and actinides. So these are called post-transition metal elements. So all these things we will see, or we will see more on these things in the later lectures. Now let's see the advantages of this long form of periodic table. So earlier in the other periodic tables, scientists were arranging the elements according to the atomic weight. Now scientists have started arranging the elements according to the atomic number. So the advantage is that no reverse order for placement in terms of atomic number. So by considering the more fundamental basis, that is atomic number, the problems of reverse order of atomic weights in placing the elements in the pairs, that is iodine and tellurium, potassium and argon, nickel and cobalt, so all these were removed. Now interpretation of properties in terms of electronic configuration. The gradual change in properties along the periods and groups can be interpreted by considering the electronic configuration, that is atomic number. No concept of subgroups and odd or even series. So the A and B subgroup, so which was in the Mendeleev's periodic table, so the convention of designation by A and B is arbitrary, but presently the metals are placed in B subgroup and the non-metals in A subgroup. So the A and B subgroup elements are placed separately. So now there is no A or B subgroups in this long form of periodic table. So hence the question of odd and even series does not arise. Splitting of triad positions. So we have already seen that in the Mendeleev's periodic table in group 8 they were keeping we were keeping three elements there. So we were calling it as triad. So now it has been removed. So though the triads are placed in group 8b, in terms of electronic configurations, they are separately grouped according to IUPAC convention. Now group 8 to 10 constitute these triads. So earlier in the Mendeleev's periodic table, we were housing three elements in group 3b. Right now we have separated them and we have given them particular groups, group 8, 9 and 10, to keep these triad elements. Next one is the positions of lanthanides and actinides. So the 14 lanthanides are not forced to be placed in a single room. In terms of electronic configurations of the 4F sublevel, the 14 lanthanides have got 14 rooms. The same thing appears for the actinides based on the electronic configurations of the 5F sublevel. So I will go back in this periodic table, and if you see, so we represent that these 14 elements, all of these 14, 14, 28 elements are here, but actually the electrons are getting filled in the F level. So F orbital. That means if you expand this, then you can find that these 14 elements are housed differently according to their atomic number. So earlier there was no proper explanation that where to put these lanthanides and actinides, but now you can give proper explanation that as the electron is going and getting filled in the F sublevel, so these will be the F block elements, and they will be housed in different rooms. So these are called rooms or house, whatever you want. Now prediction of valences and stable oxidation states. So in predicting the stable oxidation states, not the group number, but the electronic configuration is a much better criteria. So earlier we used to think that if one element is in group 3, then it will be having stable oxidation of +3. If an element is group 5, it will be having oxidation state of +5. But there was no reason of that. So now, if you see the electronic configuration, from that electronic configuration, you can say that how many electrons it will lose or how many electrons it will take. So because the electronic configuration or the atom will try to occupy a particular electronic configuration that will give its half fill or full fill nature. So those things also we will learn later. Now, interpretation of the capacity of periods to accommodate the elements. So the maximum capacity of each period to accommodate the elements can be understood in terms of electronic configuration. So as we have seen that in first period there are only 2 elements, in second period and third period 8 elements, fourth and fifth period 18, as well as sixth and seventh period 32 elements are there. But why these different number of elements in different periods? There was no justification. Right now, if you see in terms of electronic configuration, you can justify it. So if you see in first period, there is only one s. So one orbital is there. That's in one orbital you can accommodate maximum 2 electrons. So that's why the maximum 2 elements can be there in first period. Now in the second period, we have 2s and 2p. Now 2s, so it has only one orbital s, but p has 3 orbitals, px, py, and pz. So for 2s we have one orbital, and for 2p we have 3 orbitals. So in total we have 4 orbitals. Now each orbital can accommodate 2 electrons. So 4 into 2, 8. So 8 different elements can be housed in second period. Similarly, in case of third period, we can accommodate 8 elements. And if you see the fourth and fifth period, so we have D, S, and P. So this 3D, it has 5 different orbitals, which we will show in the later videos. And S has 1 orbital, and P, it has 3 different orbitals. So in total, 5 plus 1 plus 3, so 9 orbitals are there. And in each orbital, we can put 2 electrons. So 9 into 2, 18 electrons, or 18 different elements can be there in fourth and fifth period. Similarly, in the sixth and seventh period, we have F orbital, D orbital, S, and P. Now F, it has 7 orbitals. So D has 5, S has 1, and P has 3. So in total 16 orbitals are there. So if you multiply 16 into 2, because each orbital can accommodate at max 2 electrons, so we can accommodate 32 elements in this 6th and 7th period. Now we can give a proper logic that why these different periods have different elements or capacity. Interpretation of variable valency for the transition elements and fixed valency for the lanthanides. The common oxidation state +3 for the lanthanides arises due to the availability of 3 valence electrons in the outer levels. The differentiating electrons remain in the chemically inert N-2F sublevel. So let's try to understand. So what is happening when we are going to the lanthanide elements, lanthanides or actinides, the F block elements, the last electron that is going in the N-2F sublevel. For example, if you take cerium or praseodymium, the last electron will go to the 4F. Okay. But if you see the cerium's electron configuration, you will see it is 4F1, 5D1, 6S2. So although the last electron is going to the N-2F sublevel, means 4F, but it already has 1 electron in the 5D and 2 electron in the 6S. So that's why there are 3 electrons in the N-1D and NS. So these 3 electrons can be oxidized. So that's why they have a fixed oxidation state, these F block elements. So this +3 comes from the N-1D and NS. Whereas this N-2F, which is accommodating that variable number of electrons, that is kind of inert. In the same way, the common +2 oxidation state for the D block elements arises due to the NS2 electronic configurations. For the transition series, the N-1D sublevel in which the differentiating electrons are placed is not so inert. This is why the variable valency for the transition series is a common phenomena. So in case of f block element, what was happening? The last electron was going in the n-2f, and we have total 3 electrons in the n-1d and ns. So only those 3 electrons which are in the n-1d and ns, those can be oxidized. That's why they had a fixed oxidation state +3. But there is a little bit different, and the case is a little bit different in case of d block or transition metal elements. What is happening? There, in case of that, the last electron is going in the n-1d, and ns has 2 electrons, ns2. So they definitely have this +2 oxidation state. These 2 electrons can go and give it +2 oxidation state. But at the same time, they can lose electrons from the n-1d as well, because this n-1d is not that much inert. If you provide proper amount of energy, this electron can also go out. So that's why they have variable oxidation state. +2 for sure, and they can have more +3, +4, +5 according to the availability of these n-1d shell electrons. Okay, fine. Now next one is the distribution of metals and non-metals. The stair step diagonal gives an idea of the distribution of the metals and non-metals. The metals exist at the left side of the stair step, while the non-metals are placed at the right side of the stair step. What I was mentioning while showing the periodic table, and this thing also I will clear in the later videos. Still, I'll go and show it. Here, if you see this boron, silicon, arsenic, these things, boron, silicon, germanium, arsenic, antimony, tellurium, these are the metalloids. And if you take the left hand sides, those are the metals. And if you see the right hand sides, these are the non-metals. So this one is called stair step. So it is coming like this, this, this. So that's why it is called stair step. Clear? Now let's see some defects in the long form of periodic table. So the first one is dispute in the position of hydrogen. The problem regarding the position of hydrogen is not settled satisfactorily. In terms of electronic configuration, 1s1, so hydrogen has only one electron, which is in the 1s orbital. So it is to be placed in the alkali metal group. The formation of H plus also supports its placement in the group 1, but it can also form H minus, means so negative charge, say H minus, like the halogens. For example, F minus, Cl minus, Br minus. Similarly, it can also form H minus in some compounds by taking an electron. So thus, it shows a similarity with the halogens to get placed in group 17. But in fact, hydrogen differs significantly from both the alkali metals and halogens. Next defect is the dispute in the position of helium. Again, the position of helium is not settled. In terms of electronic configuration, as helium has only 2 electrons, it goes in 1s. So 1s2 is the electronic configuration. It should be placed in the alkaline earth metal group, that is group 2. But from the standpoint of the chemical inertness, it is placed in the family of inert gases in the group 18, having the general electronic configuration ns2np6. So this ns2np6 is like for the this is the common configuration for the other inert gases, but in case of helium it is a little bit exception. There is no np6, only ns2, 1s2. Thus, from the consideration of the properties, it is to be placed in the group of the inert gases, while from the electronic configuration, it is to be placed in group 2. But ideally, it is in the group 18. If you see the modern form of the periodic table, helium is placed in the group 18. But still, ambiguity is there. The next one is the borderline elements. The borderline elements lying in the border range of two adjacent blocks, that is S block and D block, or F block and D block, or D block and P block are having some properties common to both the blocks. Hence, the separation by a sharp line of demarcation cannot be justified in such cases. Next one is the detachment of F block elements from the main periodic table. The inner transition series, that is the F block elements, are thrown out from the main body of the periodic table. It indicates apparently that the members of this series do not obey the trends followed by the main body elements. Next one is the position of isotopes of lighter elements. The isotopes have not got separate rooms. For the heavier elements, the properties of the isotopes of an element are more or less the same. But for the isotopes of the lighter elements, the physical, kinetic and thermodynamic properties are drastically different. For example, the isotopes of hydrogen, that is hydrogen, deuterium and tritium, are so different in properties that to place them in a single room is really surprising. But these isotopes as of now uh, are considered to be in the same room. Now, position not always determined by electronic configuration. In the d block elements, the missing of the groups having electronic configuration n-1 d4 ns2 and n-1 d9 ns2 do not have any explanation apparently. So if you see the electronic configurations of the d block elements, you cannot find these electronic configurations. The reason actually is half fill full fill concept. So if you see n-1 d4 ns2, here d orbital can accommodate 10 electrons, but it has only 4. And if you see this one n-1 d9 ns2, d orbital can accommodate 10 electrons, it is one shot 9. So what it will do, so it will take one electron from here and will fill the d orbital, so it will become n-1 d10 ns1. Similarly, it will also take one electron from here, it will go here and it will become n-1 d5 ns1. So this is called d orbital is half filled, and here d orbital will become full filled. So this half filled full filled concept also we will learn later. So these two electronic configurations do not have any explanation apparently. Chromium and molybdenum are having the configurations n-1 d5 ns1, as I was saying, half filled. Here D is half filled, while tungsten is having the configuration n-1 d4 ns2. But still tungsten is placed in the group of chromium and molybdenum. So there is some discrepancy. So for example, chromium and molybdenum, they do this half filled and full filled concept, but tungsten is comfortable in having this d4 configuration without feeling its half filled nature, half filled D. So there is some discrepancy in the same group, but still this chromium, molybdenum and tungsten, they are in the same group. In fact, the electronic configurations for the members of 5D series, that is 6th period, differ from their respective congeners of the 3D and 4D series in many cases. But the periodic table does not care for it. This drawback is the reflection of the drawback present in the Aufbau principle. Now, what is this Aufbau principle? That will we discuss in the later videos. Maybe in video in lecture number 6 or 5. Yeah, it will be discussed in the lecture number 5 or 6. You can go and check. A similar situation arises in the inner transition series also. Thus, it can be safely concluded that the heavier elements are placed in order of their increasing atomic numbers, not in terms of electronic configuration. Yeah, so the take home message is that this periodic table, or the modern form of periodic table, that has been constructed based on the increasing order of atomic number, neither increasing order of atomic weight nor by the order of electronic configuration. It has been formulated by only the increasing atomic numbers. That you have to remember. Okay. Now let's talk about Bohr's classification based on electronic configuration. If we see the inert gas elements, for these elements, the outermost S and P sublevels are fulfilled, having the electronic configuration Ns2 and P6. Thus, the zero group or group 18 elements are the members of this family. Helium is also included here because of the fulfilled shell structure. These are generally chemically inert with respect to other elements. They generally remain as monoatomic species, among which the weak London dispersion force operates. So these inert gas elements, they do not tend to react. So if you mix different gas and if you put inert gas there, so these inert gas elements will not it will not react with the other gases or other elements. Now if you see the transition elements, these are characterized by the incompletely filled n-1 d sublevels. Evidently, for these elements, the two outermost shells are incompletely filled. Now, next one is the representative or normal elements. So these are characterized by the incompletely filled outermost shell. That is the nth shell is partially filled, while all the other inner shells are completely filled. So these actually consist of the S and P block elements. So S and P block elements are called representative or normal elements. Now what are the inner transition elements? So these elements are having n-2f levels incompletely or partially filled, along with the partial filling of the n-1d level and nth shell. So thus three outermost shells remain partially vacant in case of inner transition elements. Now let's talk about the actinide hypothesis. So for the discovery and investigation of 10 trans-uranium elements, Professor Seaborg has earned a share of the 1951 Nobel Prize in Chemistry. Now what is this? So at the early days, thorium, protactinium and uranium were mistakenly placed in group 4b, group 5b and group 6b respectively in D block. So in 1944, Seaborg pointed out this incorrect assignment and he proposed these elements to be the members of a new inner transition series analogues to the lanthanides. So this new inner transition series was described as actinides in his famous actinide hypothesis. So at that time, Seaborg was strongly criticized and warned not to publish his actinide hypothesis because it would destroy his scientific career. So see, this thing sometimes happens that if you want to publish something, if you are arguing something, so you will be criticized. The other people who are more knowledgeable or who know more in their field, they will think that you are making a mistake. So same thing happened with the Seaborg. So everyone warned him that don't say that there are something like called actinides or there are some different groups. Don't dare to publish these things. It will ruin your scientific career. So sometime later, after publishing that, so he narrated the event humorously as, I didn't have any scientific reputation, so I published it anyway. So this is the greatness of great scientists, that you believe in yourself, what you are doing, and ultimately, even in the long form of periodic table, you can see these actinides below these lanthanides. So he was right actually, but at that time people criticized him. So he used to make a humor about that and he used to say that I didn't have any scientific reputation, so I published it anyway. The actinide hypothesis saved the chemistry from a wrong direction. Seaborg and his group had synthesized many elements of the second inner transition series, that is actinides. So this much was here for this lecture 3, and in the next lecture or in the next lecture for um, in the next 3 lectures we are going to learn about the mnemonics for S block, P block, D block and F block elements. Now I am going to cover both Hindi and English. So this will be a very funny and interesting way to remember all the elements of a period or block. You can come up with your own mnemonics and you can comment down on whatever mnemonics you are comfortable with, or you can see my mnemonics also. If it is easy to remember, you can take help of my mnemonics as well. So in the next lecture, lecture 4, we will cover this all these SPD, F blocks, elements, mnemonics. And this next lecture will be divided into three parts, part A, B, and C. In the part A, I will cover S and P block elements. In the part B, I will cover this D block elements. And in the part C, I will cover D block elements along group and F block elements. Okay, so if you have any confusion regarding this lecture, you can comment down below or you can email me in my email address. If I see that a lot of confusions are arising, then I will make another separate video and I will try to resolve all your problems. Thank you. Take care.